大家好，今天的话呢是要讲一个比较面向是电脑科学跟这一个比较面向程式的一个学科了哈。那其实我不是很想花时间在这个学科，就在做所谓的深度学习的一个部分。那这一门课其实我以前在台大的时候有修过，但是没有修得很好。那时候会觉得说写程式怎么那么麻烦啊，还要自己想这个想那个啊，还是要怎么样啊？我想，因为这里的内容事实上是很多的啦，那是比较面向程式的一个部分。那我认为这门学科的话，基本上是一个你可以说简单来说，它是一个加减乘除的一个学科，你可以这么说。但是呢，你也可以说它是一个需要有一个一定的电脑的学习的电脑学科的一个学习的一个基础知识，也可以这么理解。那也列了这个6个这个关键字。那我们选读了这本书就是这个深度学习的一个基本的一本参考书是这本书Deep Learning 那 Goodfellow 还有这个 Yoshua Bengio and Courville 这些学者写的书那很厚了，我想我可能也讲不完但是希望说能够尽力的尽量的完整的把这个课文给念完。那程式的话，基本上是可能有修过这个，有学过这个资料结构的一个朋友们，或者是有学过这个离散数学这一种学科的这个经验呢，那或许呢这个学科可能会比较听得懂，或者是有学过所谓统计学啦，有用过所谓的 MATLAB，这个也是可以的。废话不多说，就稍微简单念一下这不是一个签约的一个文章这个就是一个机器学习的一个学科。大家都知道，机器学习现在有很多的应用啦，有可以辨读人声可以辨读这个可以干什么呢？可以做这个有最经典例子有蟑螂。最经典例子有这个有这个下围棋的啦，然后那不然就是这个有这个语音辨识的那不然聊天机器人那更深入的应用的话，在工厂里面有辨识这个良率的啦，点这些微博。那我在这里的话，可能单纯就是阅读课文阅读课文的部分。那这本书呢，基本上呢，我想在大学的这个图书馆可能都可以借得到可能都可以借得到。那我认为是一个或许还要有一点这个演算法跟这个线性代数的一个基础要知道说什么叫线性独立啦，什么叫对角化啦什么是这个纠敦缝点这些观念跟想法但是也不会说真的非常的难你可以也可以试着听听看，然后想说那这个是不是这个机器学习的一个观念跟想法我们就直接试试看因为内容有点多了，我当初内容有点多。Introduction. Inventors have long dreamed of creating machines that think. This desired date back to at least the time of ancient Greece. The mythical figures, Pygmalion, Daedalus, and Hephaestus may all be interpreted as legendary inventors, and Galati, Talos, and Pandora may all be regarded as artificial life. 这有学者好 Ovid and Martin 2004 Sparks 1996跟 Teddy 1997 When programmable computers were first conceived, people wondered whether such machines might become intelligent. Over 100 years before one was built, Lovelace 1842. Today, artificial intelligence (AI) is a thriving field with many practical applications and active research topics. We look to intelligent software to automate routine labor, understand speech or images, make diagnoses in medicine, and support basic scientific research. In the earlier days of artificial intelligence, the field rapidly tackled and solved problems that are intellectually difficult for human beings but relatively straightforward for computers. Problems that can be described by at least a formal mathematical rules. The true challenge to artificial intelligence proved to be solving the tasks that are easy for people to perform but hard for people to describe formally. Problems that we solve intuitively that feel automatic, like recognizing spoken words or facing in images. This book is about a solution to these more intuitive problems. This solution is allow computers to learn from experience and understand the world in terms of a hierarchical of concepts, with each concept defined through its relation to simpler concepts. By gathering knowledge from experience, this approach avoids the need for human operators to formally specify all the knowledge that the computer needs. The hierarchical of concepts enable the computer to learn complicated concepts by building them out of simpler ones. If we draw a graph showing how these concepts are built on top of each other, the graph is deep, with many layers. For this reason, we call this approach to AI deep learning. Many of the earlier successes of AI take place in relative sterile and formal environment, and did not require computers to have much knowledge about the world. For example, IBM's Deep Blue chess playing system defeated world champion Garry Kasparov in 1997, Who 2002. Chess is of course a very simple word, containing only 64 locations and 32 pieces that can move in only rigidly circumscribed ways. Devising a successful chess strategy is a tremendous accomplishment. But the challenge is not due to the difficulty of describe the set of chess piece and the allowable move to the computer. Chess can be completely described by a very brief list of completely formal rules easily provided ahead of time by the programmer. Ironically, abstract and formal texts that are among the most difficult mental undertakings for a human being are among the 这个 easiest for a computer. Computers have long been able to defeat even the best human chess player, but only recently have begun matching some of the abilities of average human being to recognize objects or speech. A person's everyday life requires an immense amount of knowledge about the world. Much of this knowledge is subjective and intuitive, and therefore difficult to articulate in a formal way. Computers need to capture this same knowledge in order to behave in an intelligent way. One of the key challenges in artificial intelligence is how to get this informal knowledge into a computer. Several artificial intelligence projects have sought to hard-code the knowledge about the world in formal languages. A computer can reason automatically about statements in this formal language using logical inference rules. This is known as the knowledge-based approach to artificial intelligence. None of these projects have led to a major success. One of the most famous such projects is CYC, Dennett and Guha 1989. CYC is an inference engine and a database of statements in a language called CYCL. These statements are entitled by a staff of human supervisors. It is an unwieldy process. People struggle to devise formal rules with enough complexity to accurately describe the world. For example, CYC failed to understand a story about a person named Fred shaving in the morning, Lin 1992. Its inference engine detected an inconsistency in the story. It knew that people do not have electrical parts, but because Fred was holding an electric razor, it believed the entity Fred while shaving, containing electrical parts. It therefore asked whether Fred was still a person while he was shaving. The difficulties faced by systems relying on hardcore knowledge suggest that AI systems need the ability to acquire their own knowledge by extracting patterns from raw data. This capability is known as machine learning. The introduction of the machine learning enabled the computer to tackle problems involving knowledge of the real world and make decisions that appear subjective. A simple machine learning algorithm called logistic regression can determine whether to recommend sensory delivery, more yourself, ETAL 1990. A simple machine learning algorithm called naive bias can separate legitimate email from spam email. The performance of this simple machine learning algorithm depends heavily on the representation of the data they are given. For example, when logistic regression is used to recommend sensory delivery, the AI system does not examine the patient directly. Instead, the doctor tells the system several pieces of relevant information, such as the presence or absence of a uterine scar, 好 Each piece of information included in the representation of the patient is known as a feature. Logistic regression learns how each of these features of the patient correlated with various outcomes. However, it cannot influence how features are defined in any way. If logistic regression were given an MRI scan of the patient, rather than the doctors formalize the reports, it would not be able to make useful prediction. Individual pixels in an MRI scan have a negligible correlation with any complications that might occur during delivery. This dependence on representation is a 这个 general phenomenon that appear throughout computer science and even daily life. In computer science, operations such as searching a correlation of data can proceed exponentially faster if the collection is tracked and indexed intelligently. People can easily perform arithmetic on Arabic numerals but find arithmetic on Roman numerals much more time consuming. It is not surprising that the choice of representation has an enormous effect on the performance of machine learning algorithms. For a simple visual example, see Figure 1.1. Many artificial intelligence tasks can be solved by designing the right set of features to extract for the text, then providing these features to a simple machine learning algorithm. For example, a useful feature for speakers identification from sound is an estimate of the size of the speaker vocal tract. These features give a strong clue as to whether the speaker is a man, woman, or child. For many tasks, however, it is difficult to know what features should be extracted. For example, suppose that we would like to write a program to detect cars in photographs. We know that cars have wheels, so we might like to use the presence of a wheel as a feature. Unfortunately, it is difficult to describe extractly what a wheel looks like in terms of pixel values. A wheel has a simple geometric shape, but its image may be complicated by shadows following on the wheels. The sum gathering of the metal parts of the wheel, the feather of the cars or an object in the foreground, obscuring parts of the wheel, and so on. Figure 1. Example of different representations. Suppose we want to separate two categories of data by drawing a line between them in the scatter part. In the part of the left, we represent some data using Cartesian coordinates, and the text is impossible. In the plot on the right, we represent the data with polar coordinates, and the text becomes a simple to solve with the vertical line. Feature produced in collaboration with David Ward-Farley. One solution to this problem is use machine learning to discover not only the mapping from representation to output but also the representation itself. This approach is known as representation learning. Learned representation often result in much better performance than can be obtained with hand-designed representations. They also enable AI systems to rapidly adapt to new texts with minimal human intervention. A representation learning algorithm can discover, discover, discover a good set of the features for a simple text in a minute, or for a complex text in hours to months. Manually designed features for a complex text require a great deal of human time and effort. It can be takes decades for an entire community of researchers.这个 quite essential example of the representation learning algorithm is the 这个 autoencoders. An autoencoder is the combination of the encoder function which converts the input data into a different representation, and the decoder function which converts the new representation back into the original format. Autoencoders are trained to preserve as much information as possible when an input is run through the encoder and then the decoder. But they are also trained to make new representation has various nice properties. Different kinds of autoencoder aim to achieve different kinds of properties. When designing features or algorithm for learning features, our goal is usually to separate the factors of variation that explain the observed data. In this context, we use the word factors, simply to refer a separated source of influence. The factors are usually not combined by multiplication. Such factors are often not quantities that are directly observed. Instead, they may exist as either 这个 unobserved objects or unobserved forces in the physical world that affect observation quantities. There may also exist a construct in the human mind that provide use for simplifying explanations or inferred causes of the observed data. They can be thought of as concepts of abstraction that help us make sense of rich variability in the data. When analyzing a speech recording, the factors of variation include the speaker's age, their sex, their accent, and the words they are speaking. When analyzing an image of a car, the factors of variation include the position of the car, its color, and the angle and the brightness of the sun. A major source of difficulty in many real-world artificial intelligence applications is that many of the factors of variation influence even simple pieces of data. A simple piece of data we are about to observe. The individual pixels in an image of a red car might be very close to back and line. The shape of the cars 这个叫做sharehold depends on the view angle. Most applications requires use to disentangle the factors of variation and discard the ones that we do not care about. Of course, it can be very difficult to extract such high-level abstract features from raw data. Many of these factors of variation, such as speaker's accent, can be I tend to find it only using sophisticated, nearly human-level understanding of the data. When it is nearly as difficult to obtain a representation as to solve the original problem, representation learning does not at first glance seem to help us. 好，我们就念到这里啊。那这里有一些词 ，artificial intelligence 叫硬库机率 ，deep learning 的话是特罗尼 ，knowledge base 是知识期盼 ，logistic regression 是这个路基是体回归 ，representation 是票hiệu，那 encoder 的话是 encode 哦。感谢各位收看啊。